today we have two young scientist presenters, Sauradeep Majumdar and Una Trivanovic. And we would like to invite Dr. Yen Ning, the Dean's Chair Associate Professor of the National University of Singapore, to chair the session. Dr. Yen, please.
All right. Good evening, everyone. I'm Ning. Now I'm working in National University of Singapore in the Chemical Engineering Department. But before I come to NUS, I spent 4 fabulous years in Switzerland. So that gives me the great pleasure to introduce 2 presenters, young scientists that are going to give the presentation. Both of them are coming from Switzerland. And that reminds me of my wonderful student years. The first presenter is Sauradeep Majumdar. He's a doctoral student at the Swiss Federal Institute of Technology, Lausanne. His research interests include computational chemical engineering, molecular simulations, machine learning, and carbon capture. Allow me now to hand the time over to Sauradeep. Yes, please.
Am I audible? Really? Okay, so hello everyone. Very good afternoon, evening, morning to whichever part of the world you are all joining from. Today I'm very happy to be here and share a little bit about my PhD research, which is titled Finding Promising Nanomaterials for Energy Applications Through a Diversity-Driven Search. Okay, now many of you might have come across similar images or news articles in the last few years. And in this context, I would like to share a personal story. This is probably last summer of 2022 when I was talking to my family in India, and we were discussing about temperatures in Switzerland. And I was telling them that today the temperature is around 38 to 40 degrees Celsius. And my parents thought that I was joking. Because typically when you speak of Switzerland, the images which come off is something like this, a white area, glaciers, mountains, snow, and they're right in their own way. But then this happened again and again and again for days, for weeks, for months. And this experience then kind of made me realize how climate change is actually affecting small parts of our daily lives. And then that made me thought that yes, this is something no more a mythological concept as such, and yes, it's no more something which I'm just reading in an environmental science book, and this is how what I'm experiencing, to the point that some days of the summer of 22 became just unbearable. So then how are we tackling it, or how are we going about it? If I speak from a scientific community point of view, there are mainly 2 broad ways in which we are kind of tackling climate change. The first one would be we kind of shift completely from fossil fuels to renewable energies. That's a very active field of research. But then till the time renewable energies reach the level of providing the rising energy demands of our population, it will still take many decades, and for all those decades there still will be emissions of CO2, which is a primary contributor to climate change. And that is where comes the second round of, or the second route of tackling climate change, which is carbon capture, and which itself has its different ways of capturing CO2 from industries, directly from air, and many other areas. Now, whichever route we go in, one very central part which is an important key in both the routes are materials. People have been researching in different classes of materials, be it 2D materials, 3D materials. People have been working on graphene, activated carbon, zeolites, different framework materials, a huge range of materials. But the specific class of nanomaterials which I am going to focus in today's talk are metal organic frameworks, or MOFs in short. And before I proceed further to discuss about MOFs, just a quick question to have a rough gauge. How many of you have probably come across the term MOFs, or metal organic frameworks? Okay, not bad, some of you. Okay, so for those of you not aware, a MOF, or a metal organic framework, consists of a metal part, a metal node, an organic linker which is connected together in form of a template or a network which we call topology, which then gives rise to these beautiful nanocrystals. Over the last 2 decades, MOFs have found themselves to be very useful in a wide range of applications like gas energy, gas storage, catalysis, drug delivery, sensing, and many more. And a big reason behind it is that it consists of a very interesting combination of a wide range of properties. For example, it has really high surface areas, and to give a context of this, just 1 gram of a MOF can cover an entire football field. So it has surface areas ranging up to 5,000 meters square per gram. It has pore sizes which enables to trap different gases like say CO2, N2, and therefore put them inside their cages. It also has tunable chemistries. For example, if you by combining these metal nodes and organic linkers and in different topologies, really infinite amount of MOFs can theoretically be made. And all of this has led to over 100,000 experimental MOF structures being synthesized over the last 2 decades. And with the advancement of computational techniques and simulations, we also have millions of hypothetical structures which have been generated in silico. Okay, so far so good. We have millions of materials, we have computational power, we screen them, we try to find the best materials from the screening. But this also creates a dilemma for this entire MOF community. The dilemma being that on one hand, at present, we have so many materials that even if we have the fastest computer on the planet, we cannot end up screening millions of these materials. But on the other hand, as I mentioned, theoretically, an infinite amount of MOFs can be actually be possibly made. So that is what is represented in this graph. I will come to the technical details of this graph in the subsequent slides, but for now, what I want you to take from this slide is that this kind of represents these gray dots which you see, kind of represents unexplored areas of the material space, the material MOF chemical space, which we haven't explored that much, but a MOF can possibly exist over there. So then how do we create a balance between these two contrary search? Because a holy grail of material science has been to find the most optimal material for a given application. And therefore, we decided that we need to take a different approach from the brute force screening, and we decided that we're going to take a diverse sampling of this MOF chemical space and create a diverse database of materials, screen them, and then find, instead of finding the best one material for a particular application, we want to locate what is the most promising regions or the best regions of the space which contributes to a material being good for that application. And once we find that interesting region of the MOF space, we can then populate that area with different techniques. And for that, we developed a computational workflow comprising of different techniques using molecular simulation, machine learning, and material design. I'll just briefly, I don't want to go into too many technical details, but just briefly give you a glimpse of what this Morph World might look like. So for example, here you are seeing the building blocks of these materials, or what we also refer to as the genes of these materials. So on the left-hand side, you see some of the metal nodes. On the right-hand side, you find some of these organic linkers. Then you can functionalize the organic linkers with different functional groups. And this whole range, along with networks and topologies, create a very high-dimensional space. And with this, we created an in silico database of around 20,000 materials. And once we created this database, we wanted to visualize that if at all there was a material space or a universe of materials, how would it look like? But then it's a 200 or a very high dimensional space. So how do we visualize the 200 dimensional space? We can't make sense out of it, right? So what we did is that we used machine learning techniques to reduce this high dimensional 200 space to a 2-dimensional space to get a rough idea of if this universe of materials did exist, how would it look like? And what you can see as a glimpse over here is that each point in these graphs represents a material. Wherever you see a colored dot in terms of the Morph components, so for example, this represents the metal part of the Morph, this represents the organic linker chemistry of the Morphs. So the colored dot represents those areas which we have sampled from the known chemical space of Morphs, and in each plot you will find there are some gray areas that represents the unexplored or the relatively less explored areas of the Morph material space. It's like, imagine you have this galaxy and this universe of different materials where certain materials exist, but we have still not set our foot onto it. So to me, the way I see it is that, hey, this is one aspect of Morphs, like say for example, the geometrical properties of materials which we have explored quite well. But the other areas, we need to work harder. For example, metal chemistries, we can do much better. And in this way, we iterated, we made many iterations, we tried to see what is it that we can improve the diversity, and then we developed different quantifying techniques to show how adding our materials improved overall diversity of this Morph community. And I'm not going into the maths of all these things, but this is just to see that how diversity was a tool in this particular aspect. Okay, so far so good. We are visualizing, we are having this database of materials, but then we thought, now that we have these materials, can we use it for some practical applications, or does it just get limited to a theoretical concept? So one of the applications which we are really interested in was carbon capture, and what you see again is a small example of 4 of the metal clusters which we used, and you'll find the histograms of different materials, and in each plot you'll find a blue line. The blue line basically represents the reference line for zeolite 13X, which is a commercially available carbon capture adsorbent, which is used in many industries, the oil and gas industries, the coal power plants industries. And we wanted to see that if any of our material is better than the current existing material. So you can see, for example, Morphs made of these kind of metal nodes are practically useless for our application, because hardly any material or a very, very few percentage of materials are better than the benchmark. But then Morphs from these materials, we have quite a few interesting candidates. And that is how we came to also find another similar candidate which was not in our initial list, but we went back to this plot and we tried to say that, okay, if this is an interesting region of the space and if we find a dot over here, then there should be some materials around here which will also be interesting. And that is how we also came to find this particular metal node. And we extended this to even other applications. We extended it to hydrogen storage, we extended it to methane separation, and the thing which I liked most about this thing was my initial aim was not to find best materials for hydrogen storage. I was only focusing on carbon capture. But since we did a diverse sampling of this entire space, some parts of the space contributed to materials being good for carbon capture, but some parts of the space contributed for a material to be good in hydrogen storage. And those two material lists may not necessarily overlap, like the materials good for this application may be absolutely useless for this application, but the diverse sampling helped us locate that region. So if I just summarize the overall computational workflow which we have used over here, we start with the genes of a material, which is the building blocks. We build a material from there. We then create databases of these materials, experimental, computational. We screen them using different computational techniques and try to find out which are the promising materials for, say, an application like carbon capture. And then we also now going one step ahead and testing these materials in real industrial conditions and trying to see that which of the materials actually last in the final industrial cycles. And in order to help us in our aid to search this huge infinite dimensional space more effectively, we are taking the help of machine learning techniques where we're trying to map directly from this genes of a material to the final application and the property, so that we can find out and say that what is it in a material. Is it the metal chemistry? Is it the linker? Is it the particular bond between the metal and organic linker? Or is it the orientation between the 3D structure of a morph which makes it good for a material? And that helps us to enable to design even better materials for next generations. Thus, in this study, what we show that is even if we start with a relatively small but a diverse set of materials, we can still obtain promising material for different applications. And once we locate that interesting region of that material space, I keep repeating this word material space so that we have that visual thing in our mind that we are setting our foot into unexplored regions, we can then explore around those interesting regions using different techniques, mathematical and physical techniques. And this thus also helps in a broader goal of materials discovery, thus extending it to many other classes of materials also. And with this, I'd like to thank my supervisor, Professor Baron Smith at EPFL, and my lab members, and all my funding agencies, and last but not the least, all of you for your patient hearing. Thank you.
Thank you. Thank you, Sauradeep. Now we
you can just move there and ask. Yes.
So I also I also asked something about machine learning and the Morphs for the application. My question is, so the machine learning exists for the Morphs. So for the simulation of the Morphs has existed in the database, or so can we got a principle for the application? For example, for water stable. For the CO2 absorption with the water stable Morphs. So my question is that the machine learning is from the existing Morph or the new, or can predict new Morphs?
It's both ways, I would say. So one thing is that for existing Morphs, for like experimental structures, we try to predict, like for example, in the example you say, like say for example, you have a water stable, like whether a Morph is stable in water or not, that can be predicted for experimental structures, and I believe that is a thing which has, I think, is being done now at quite a good level. And the next level which we are trying to solve is, can we predict structures? Like for example, using concepts like inverse design. Like for example, can we design structures and predict a structure which we know a priori will be good in water or stable in water or in a realistic flue gas condition? Okay. Was that your question? Sorry.
Okay. And then we can synthesize the predicted Morphs for the experimental to verify the properties.
Synthesis is a thing which goes parallelly, yes. I mean, of course, I wouldn't say that all the Morphs which we predict theoretically get synthesized. Of course, I wouldn't say that. But yes, there have been many examples also in recent years where many of the Morphs which have been theoretical. So typically what we do is that maybe from millions of structures, we would probably give my experimental colleague 50 structures, that these 50 are probably the best out of 5 million structures. And then the experimentalist, maybe out of those 50, maybe 30 of them will be discarded because, I don't know, expensive linkers or some other issues and all, maybe only a few of them will be made. So if you are speaking of the percentage, yes, the percentage is few, but then it helps us just navigate the space better, I would say.
Oh yeah, thank you very much.
Thank you, Bhagwesh.
Hi, also thank you for the presentation, and what I particularly enjoyed is your use of visualizations. In particular, you were using TSNE, dimensionality reduction method, to visualize basically the, let's call it the material space, right, that you're visualizing. Did I understand correctly that you were also using this visualization to identify new areas where you want to search for new materials that have not been discovered before?
Yeah, so for example, I showed about, so there are different dimensionality reduction techniques. So we have principal components, we have TSNE and all. So since I mentioned that we have this, say, a 200 dimensional space, so especially in the case of PCAs, once we get a coordinate of a particular space with respect to a particular feature of a Morph, we can locate what is the nearest other Morphs which are near to that point, because similar materials will be located similar in the material space. So that was the philosophy of finding new materials. So probably something lying out there which we didn't sample first, and then we take out from there and make a material out of it.
I find this very fascinating. I've also used UMAP before for similar
Yes,
purposes.
UMAP is one more technique. I haven't used it, but yes, that's also one more good technique.
A question that I have, which is like a common limitation of TSNE or UMAP in that sense, is that they are not necessarily distance preserving in the original space. So
you are correct.
I'm also asking myself if one can today rigorously argue about the search method when we have no guarantees that we're actually preserving distances in the original space.
Yeah, that's a really interesting point. I mean, yes, of course, there is no guarantees because the TSNE and UMAPs are also based on statistics. whereas principal components on that aspect preserves the global variances much more. So from a principal component point of view, I've shown only the Tesla maps over here, but we also had a principal component analysis, and along with that we also what we call, or I would term it as chemical intuition, which like you combine your chemical intuition along with the machine learning data to come up with that morph. Like, okay, so what kind of metal atom, what is the oxidation state, what are the type of connection points, what kind of linkers, what are the other properties, and to have a similarity index. So I would say it's a combination of the machine learning techniques and the scientist's own intuition, which would probably go forward to select a material.
Okay, very cool. Thank you so much.
Next, please.
Thank you for the talk. My question is, does the machine learning able to predict some of the limitation on like the synthesis? Like, for example, like, you know, like some of the structure maybe is thermodynamically unstable to be synthesized, that like the cavity is just too large. And if it doesn't, is there anything that you can do in the future so that the machine learning is able to predict like those limitations, so that, you know, whatever is being predicted on the material, it is actually possible to synthesize it experimentally? Thank you.
Yeah, one work which was very recently published was actually in this area where natural language processing tools, like for example, something which Google and Microsoft uses, in those lines, all the experimental data from the last 2 decades were actually used as training in a group, and they tried to predict what is the thermal decomposition temperature for the MOFs. So for example, till what temperature are the MOFs stable? So this was, I think, in this field quite a good leap. So it, of course, it won't give you the guarantee that, of course, if a MOF is stable, it will be made for sure. That will still take some time, but at least there are efforts being made, and I'm hopeful that it will be going in that direction. At least till now, we can give a rough indication that, okay, till what range of temperature is this MOF stable, and when does it start to degrade? And then maybe study in more detail the few character structures which we are not very sure of.
Thank you.
Any further questions from the audience? Perhaps I can ask your question while the audience consider more. My first question is general. You are a PhD student.
Yeah.
So far, what do you enjoy the most about your PhD, and what do you dislike the most?
Okay. I think it changes with the year of my PhD. Every year the likes and dislikes changes, but yeah, if I kind of sum up, I mean, I think PhD in a way helps. So I'm coming from a chemical engineering background. I did my bachelor's and master's in chemical engineering. I worked in industry. So I've always been in a more application oriented field, like always in a thing. And I wanted to experience this other side where you can actually use creativity and combine it with applications to have a greater degree of freedom. So this is one thing I really enjoyed, that, for example, the example with visualization. So for example, finding something through a mixture of creativity and sense of application. I think this is a freedom which academia to some extent gives us, and at least in my PhD, I really liked it. Dislikes, yes, of course, there are many. Of course, there is probably, I'm working with some statistical thermodynamics. So we often use these error bars, right, in many of our measurements. And I find that, yes, the uncertainties are so huge sometimes in whatever things we do, that maybe we work probably many years, maybe something comes out, maybe something not comes out, especially in my first or second year of PhD, that sometimes got me derailed or demotivated. So that was the hard part, I would say. And yeah, so I'm lucky that somehow I managed it.
Okay. Okay, good. So the thing you enjoy the most of your PhD is you are able to really work on projects with application perspective that use fundamental knowledge, fundamental creation. Yes. You can solve really grand practical challenges.
Yes.
And the thing you dislike the most are some actually technical limitations, some frustrations,
yeah.
the more detailed process. Okay. I have one more question for you. You are doing simulations and machine learning. Do you fear your work has to be sooner or later combined with experimentalist work, and how are you going to achieve that?
Yeah. So yeah, this is something which definitely goes on in my mind. And for example, in one of the current studies I'm doing, actually, one of my experimental collaborators actually was able to synthesize one of the materials which we made. And of course, it was a difficult task in general, like combining simulations and experimentations, because you need a lot of trials and stuffs, and things may not always go well. It is something I would say, I won't say it's a fear, but yeah, it is definitely something which I keep in my mind when I'm working on my future projects, or if I'm thinking of starting a project or working with project, that how to kind of link it to an experimentation. Sometimes it doesn't work, like probably because of different factors. But yeah, there was like few examples where it did work, and yeah, that was good.
Okay, thank you very much. Is there any final question from the audience? Okay. If not, please join me to thank Sauradeep one more time for his presentation.
Thank you.